The next mode of heat transfer that we are going to discuss is radiation. Okay. We call it as thermal radiation, which is basically transfer of energy from one place to another by a different means. We'll discuss how it happens. Okay. Consider this example. We all know from everyday experience that we receive heat from the sun. Earth receives heat from the sun. Can any of you tell me how this transfer of heat is taking place? Is it through conduction? First question. Heat getting transferred from the sun to the earth, is it through conduction? I got one answer as no. How can you tell for sure that it is definitely not conduction?
Sir, because in space no matter is present.
Okay. Between the sun and the earth, there is vacuum. There is no medium present between them. There are no molecules present between them to transfer heat layer by layer. So, heat transfer from the sun to earth is not taking place through conduction. Okay. Then, how exactly are we receiving heat from the sun? We receive light also. Okay. And there is a relation between heat and light. We will discuss all that in this chapter itself, or in this part of the chapter itself. Basically, what happens is the sun emits radiation. Radiation is nothing but electromagnetic waves. Okay. Waves always carry energy with them. Okay. So if anything emits waves, whether it's electromagnetic waves, light waves, sound waves, okay, or any other kind of wave. So you can have mechanical waves also, waves on the surface of water, waves in a string, such things, such examples. In any kind of wave, there will be transfer of energy. So basically, what happens is the sun emits electromagnetic waves. Okay, and it emits electromagnetic waves in all directions, some of which reach the earth. Okay, fine. This is how we receive heat from the sun. Okay, how the earth or any other planet also receives heat from the sun. So not just from the sun, from objects that we find in everyday life also. Okay, sun is also an object found in everyday life, fine. The other objects that we find on earth also, there will be energy emitted in the form of electromagnetic waves. Okay, and that is what we call as radiation. Okay, so this is what we are going to study about. Now, what exactly is an electromagnetic wave? How much energy an electromagnetic wave particularly carries and all? There is a separate chapter dedicated to that. We are going to look at the heat transfer aspect of it. Okay, like through electromagnetic waves, how much heat an object can release in a certain amount of time, how much heat an object can receive in a certain amount of time. Those are the things that we are going to discuss. Okay. Uh, can any of you tell me how vision works? How do we see objects? Like, I'm sure most of you must be holding a pen. How do you see the pen?
The light from the object gets passed on to our retina.
Okay, you consider the pen itself. Is the pen emitting its own light? Others can also answer. How do we see the objects around us? Or how are they becoming visible to us? That is the question. Sohan, is the pen emitting its own light?
No, sir.
Okay. Then from where is the light coming?
It reflects the light from sources like sun, tube light.
Okay, good. Correct. So most of the objects that we see basically reflect light into our eyes. And that is how we perceive there is an object present there. Okay. Now, light from a source like the tube light or maybe sunlight, any other case, any other source also. Light from a source falls on an object. Some of that light gets reflected. Okay, fine. Now, in most of your houses or rooms, the tube light will be white in color. Okay, the ambient light will be white. Sunlight is also almost white. Fine. So, how we see most of the objects around us is energy, light from the source falling on the object and getting reflected. And reflected light, when it enters into our eye, will be able to perceive that there is some object present in that direction from which the light is entering into our eye. Fine. Suppose there is an object which appears blue in color. Okay, like maybe the ink that you are using could be blue. Okay, or there is some other blue colored object. Maybe the jeans that you are wearing could be blue. So suppose there is a blue colored object. Now the light falling on the object is white light from the tube. Okay, when white light is incident on this object, how is the object appearing blue? We just discussed, or some of you just told, that light from a source falls on an object and gets reflected. That is how we see objects. Okay. If white light is falling, then why does the object appear blue to us? Or any other color also for that instance. You may be seeing some red colored object around you, some brown colored object. The table that you are using could be brown in color. When the light which is incident on that object is white, why does the object appear to be of a different color? Everything should appear white to us. Think carefully and answer. I'll give you a minute. Okay. Yusuf, your answer is correct. White is basically a combination of many different colors. Okay. White is not a separate color actually. When red, green, and blue of equal intensities enter into our eye, we perceive it as white. Fine. So white color is actually a combination of many different colors. When white light is incident on an object, it means many different colors are incident on that object. Okay. Now, the object appears blue to us means the light reflected by the object. Let's say this is the observer's eye. Fine. The light reflected by the object is blue. Okay. Since the page here is white, I indicated white light with a black arrow. I think that is understood. So white is basically a combination of colors. Fine. And each color has a wavelength corresponding to it. You will learn about that in electromagnetic waves in your 12th class chapter. So when many different colors are incident on an object, let's say this object appears blue to you, that means it's reflecting only blue light or blue color. What is happening to the other colors? They are getting absorbed. Okay. So basically when light falls on an object, some of the light gets absorbed and some light gets reflected. Okay. If some object is appearing yellow, that means it is absorbing all other colors, reflecting only yellow color. Okay. Or wavelength corresponding to yellow color. That is what is happening. So in general, when energy is incident, okay, or when radiation means electromagnetic waves, okay. Now I'm talking about radiation, and then I'm talking about light. Light is also radiation itself, electromagnetic wave itself. Okay, you must have learned this. Light is an electromagnetic wave. So each color that we see has a particular wavelength associated with it. So when radiation is incident, okay, radiation incident means what? Electromagnetic waves are incident on a surface. Some of it means some of the radiation is absorbed by the surface and some of it is reflected. Okay. Now, based on how much of the incident energy is absorbed, we can define a quantity called absorptive power of the surface, denoted by the symbol small a. Basically, it is the ratio of energy absorbed to the energy incident means what fraction of incident energy is absorbed by the surface. That is what we define as the absorptive power of that surface. Okay, hope the definition is clear. It's not very difficult to understand also. Every surface has certain amount of absorptive power. Whatever energy is incident on it, some part of it will be absorbed, remaining will be reflected. Okay. Now, based on this definition of absorptive power, the formula of absorptive power, you tell me what is the absorptive power of a perfect absorber? Perfect absorber means what? A surface which absorbs all the energy incident on it. How much will be the absorptive power of that kind of a surface?
The one.
Obviously. Okay. If it absorbs all the energy that is incident on it, energy absorbed will be equal to energy incident, then the absorptive power of that kind of a surface will be equal to 1. Good. Next. Okay. I want someone else to answer. What do you think will be the absorptive power of a perfect reflector?
0.
0. Okay. From the name itself, it is obvious. Perfect reflector means it does not absorb any energy. It reflects all the energy that is incident on it. Okay. Then energy absorbed will become 0 for any non-zero energy incident. Okay. Then the answer becomes 0. Absorptive power becomes 0. Okay. So remember, absorptive power is just a ratio. It's not an actual power because basically mechanical power is defined as energy per unit time. Okay. Or work done per unit time. Units are watts. Okay. Absorptive power is not that kind of power. It's just the fraction of energy that a surface can absorb. Okay. So it won't have any units or dimensions. And you can also remember that it ranges from 0 to 1. So for any surface, 0 less than or equal to its absorptive power less than or equal to 1. It cannot be outside this range. Okay, fine. So when radiation, okay, radiation means electromagnetic waves, for example, light. Okay, so when radiation is incident on a surface, some part of radiation is absorbed and some part is reflected. Basically, that happens with every surface. Okay. Do you think we see all objects due to this phenomenon itself? Like when I asked you how we see objects around us, some of you said that light from a source, like the tube light or the sun, falls on an object and gets reflected into our eyes. Okay, and that's how we see objects around us. That is one way. That's okay. Is there any other way by which objects are visible to us? Reflection of light from a source is one way how objects become visible. Is there any other way in which objects become visible?
The objects absorb energy and then emit energy waves.
Okay, so you are saying they emit their own light instead of reflecting. Is that what you are saying?
Yes.
Okay, okay, that is correct. See, basically, to see some object, we need light from that object to enter into our eye. And there are two ways that can happen. That object can reflect light, that object can emit its own light also. Okay. For example, you consider this incense stick. Okay. Agarbatti. Do you think this will be visible in a dark room? If it is not, what do you call, ignited or lighted up, do you think this will be visible in a dark room? Obviously not. Okay. It will not be visible. You can just consider a rod also. Okay. A metal rod at room temperature. A metal rod at room temperature will not be visible in a dark room. Fine. Same with this. So this is not visible in a dark room. Why? Because in a dark room, there is no source of light and this object does not emit its own light. Okay. What if you light up the incense stick? Let me uh, show it like this. Suppose we light up the incense stick. Let's say it is like it has been ignited and Maybe it is producing smoke also. Now, will this be visible in a dark room or not? Obviously, it will be. You must have experienced this also. Okay. What's the difference between an incense stick which has not been lighted up and one which has been lighted up? Can any of you tell me? Like we are talking about heat transfer and all. So in terms of uh, whatever quantities we discussed in these chapters, what is the difference between these two incense sticks? Okay. Can any of you tell me what is flame? Flame or fire? What is it? Like you light up a matchstick, you can see flame. Okay. Basically, what is that? Okay, fine. See, the basic difference between the incense stick which has not been lighted up and the one which has been lighted up is the temperature of its molecules. Obviously. Okay. So you can just consider a metal rod also. A metal rod at room temperature, if you switch off the lights, it will not be visible. But if you heat it to sufficiently high temperatures, it turns red hot. Same thing happens with incense stick also. If you heat it to sufficiently high temperatures, the molecules there turn red hot and it will be visible in a dark room as well. So basically what is happening is the incense stick, once it is lighted up, it is emitting its own radiation, which we can see. Okay. It is emitting waves, electromagnetic waves with wavelength corresponding to red color. Okay. That is why it appears red. Okay. Or orange to us. There's a particular wavelength of radiation that it is emitting. Fine. For every color, there is a wavelength associated. I can, I mean, in fact, you have to remember this also. Now, we know there are seven basic colors which you are. Okay, fine. Let's say this is violet. The wavelength of electromagnetic waves, okay, which correspond to violet color is around approximately 400 nanometers. Nano is 10 power minus 9. Okay. So an electromagnetic wave whose wavelength is about 400 nanometers, if it enters into our eye, we perceive it as violet color. Okay. The rods and cones in our eyes, they oscillate in such a way that we feel it is violet. Next, the other extreme, red color, if you consider the wavelength corresponding to red color is close to 700 nanometers. Okay, some books write it as 680, some write it as 720. It's around 700. Exact value you will not be asked. Okay, and the other colors lie in between these two. Okay, so electromagnetic waves which have wavelengths ranging from 400 to 700 nanometers are the ones which show us colors. And there can be combinations of colors also which appear as new colors to us. Okay, for example, if you mix blue and red, you get pink. So that is also possible. If you mix all colors, you get white. Okay, or like if light of many different wavelengths ranging from 400 to 700 enters into our eyes, we perceive it as white. Okay, so this set of wavelengths of electromagnetic radiation, which is basically visible to us, is called the visible range of wavelengths. From here, 400 nanometers to 700 nanometers. This is called the visible range of electromagnetic waves. Fine. What about electromagnetic waves whose wavelength is less than 400? The waves whose wavelength is less than 400, even if those waves enter into our eye, we will not be able to perceive anything. Human eyes are not designed, or human brain is not designed to, uh, what do you say, understand those waves. Fine, but such waves do exist. Okay, waves whose wavelength, electromagnetic waves whose wavelength is less than 400 nanometers, they exist. They are very common. They are called ultraviolet waves. Okay, so wavelength less than 400, you call it as UV, ultraviolet range. All electromagnetic waves of wavelength less than 400 fall in this range. Okay. What about electromagnetic waves whose wavelength is more than 700 nanometers? Such waves also do exist. Okay. And when those kind of electromagnetic waves enter into our eyes, again, our brains are not designed to understand those waves. Okay. We don't perceive anything at all. Fine. They are called infrared waves, IR. Okay. And that range of wavelengths is called the infrared range. So all possible wavelengths of electromagnetic waves, okay, can be split into three broad categories like this. Very short wavelengths, electromagnetic waves having very short wavelengths. Very short means less than 400 nanometers, fall in the ultraviolet range. They are not visible to us, but these are high energy radiations, extremely high energy radiations. And usually, when ultraviolet waves are incident on human skin, okay, or human cells, and not just human, I think any living cell, okay, when ultraviolet radiation is incident, the energy of the radiation is so high that it can damage the cell, it can damage the DNA. Okay, it could cause mutations in DNA, which ultimately leads to cancer. Okay, that is why ultraviolet radiation is harmful to us, and we need the ozone layer to protect the ultraviolet radiation emitted by the sun. Okay, we have discussed at the starting of this lecture itself that we receive energy from the sun in the form of electromagnetic waves. Okay, those electromagnetic waves produced by the sun will be a combination of ultraviolet plus visible plus infrared. Okay, so high energy radiations will be there, moderate energy radiations will be there, low energy radiations also will be there. The ozone layer blocks the high energy radiation, or at least most of it is blocked. Okay, ultraviolet radiation is blocked. Visible infrared do pass through the ozone layer and reach the surface of the earth also. Okay, and there are some planets which do not have an atmosphere at all. Fine, or they may not have an atmosphere which is dense enough to block sunlight or some part of sunlight. On such planets, life itself will be difficult to exist, because if UV light is directly incident on a planet, it is difficult for life as we know it to exist on that planet. Right? There may be some cells which can withstand those kind of radiations. Such cells can survive, but the the living cells that we find on Earth, it is difficult for them to survive UV rays. Okay. Of course, it depends on the intensity of radiation. Small amounts of UV cells can bear that, but uh, if the intensity is higher than a certain threshold, then the cell will definitely get damaged. So remember that UV radiations are low wavelength but high energy radiations. Okay, energy is inversely proportional to wavelength. You'll learn this in another chapter. As I said, there's a separate chapter dedicated to electromagnetic waves in your 12th class. In that, you will learn. Okay. Then the other extreme, if you see infrared range, infrared waves are extremely low energy waves. So even if these waves, light, I mean, visible range and infrared range, the living cells can bear. So they won't damage the DNA and all. Ultraviolet rays damage DNA. Okay. This visible range of electromagnetic radiation is basically what we call as light. Okay, visible light. Fine. Now let's go back to that incense stick example. At room temperature, the incense stick or its molecules will not be visible in a dark room. But when you light it up, basically what you're doing is increasing its temperature to a certain value. When you increase its temperature to a certain extent, it becomes visible. It starts emitting visible radiation. Emitting visible radiation means what? Emitting electromagnetic waves whose wavelengths are in the range 400 to 700 nanometers. Okay, it starts emitting in that range. Okay. Does that mean the incense stick before it was lighted up was not emitting anything? No. Now, you might have heard of something called night vision goggles, or you might have heard that dogs can see even in dark. Have any of you heard things like that? Okay, some of you have raised hands, and that is correct. There are something called night vision goggles. Okay, and there are some animals, not some, there are many animals which can see in the dark also. They can see or they can perceive radiations which we humans cannot. Now, how does that work? Basically, their eyes and their brains are designed to respond to low energy radiations. Okay. So what happens is at room temperature, this incense stick that is there, or any other object also you can consider. At room temperature, the object will be emitting radiations, but not in the visible range. Okay. Basically, it emits, the object at room temperature emits low energy radiations. Means what? Infrared radiations, which human eyes and brain cannot perceive. Okay, but you can make machines which can receive those waves and react to those waves. That is how night vision goggles work. Okay, and there are animals which can perceive those waves also. That is how some animals see in the dark. Okay, actually see. Fine. Now, when temperature is raised to a sufficiently high value, the object, the same object, starts emitting radiation in the visible range. That is when it becomes visible to us humans. Okay. Now, you might have seen metal being heated, or you can try it also. You take a metal wire or a metal rod, put it on flame. Metal rod at room temperature will not be visible in a dark room. But if you put it on flame for a sufficient amount of time, you will see that the metal rod turns red hot. Okay, suppose this is the rod. Let's say you put it on flame for sufficient amount of time. Just a moment. Okay. You will see the end, which is close to the flame, turning red. Of course, a color gradient will develop. So that end will turn red. Now you continue heating it. If you continue heating it, you will also see that after some time, it even turns yellow in color. Okay. After some time means when its temperature rises to sufficiently high values, you will see it turning yellow as well. Yes or no? Have any of you observed this, at least seen in videos, metal being heated? Okay. I'm sure most of you must have seen this. And I asked about what is flame. Okay, you can see a cartoon image here of flame. You might have observed flame from a matchstick, flame from a gas stove. Okay, flame is also of different colors. I'm sure you must have noticed that. Now, what is basically happening here? See, the metal rod as such is not visible in a dark room, but once it is raised to sufficient temperature, means when you start heating it, once it is raised to sufficient temperature, it turns red in color first. Means it is emitting radiation of red color. Okay. Red color has wavelength around 700 nanometers. So it starts emitting that radiation. Okay. As you continue heating means what? Continue rising its temperature. Okay. So when temperature rises to a certain value, sufficiently high value, you will see it emitting yellow color. Okay. It appears yellow to us means it is emitting yellow colored radiation, right? So what this shows is as the temperature of an object rises, okay, the energy of radiation emitted by it also rises. Now you can observe here from infrared, when you go to ultraviolet, energy is increasing, energy of radiation increases. Okay, wavelength decreases, but energy increases. And based on what we observe when an object is heated, we can say that as temperature rises, the radiation emitted by it will be of higher and higher energies. Okay, hope this is clear to all of you. Now, actually, what happens is any object at any temperature will actually be emitting all possible radiations: ultraviolet, visible, and also infrared. Okay, even an incense stick which is not lighted up, which is at room temperature, not just incense stick, any other object you take, maybe the pen that you are holding also, at room temperature, it will be emitting radiation of all possible wavelengths. Okay, so any object at a temperature greater than 0 Kelvin, means greater than the absolute zero of temperature. Any object at a temperature more than this, okay, every object that we see in daily life is at a temperature more than 0 Kelvin. Fine. So any object at temperature greater than 0 Kelvin emits radiation. Radiation means what? Electromagnetic waves, okay, of all possible wavelengths. Fine. All possible wavelengths include visible wavelengths also, right? Then why don't we see objects? Why don't we humans see objects in a dark room if it is emitting visible light? Can any of you answer this? This statement is correct. Any object will be emitting radiation of all possible wavelengths, but why don't we see objects in a dark room? Why don't we see all objects in a dark room? Think and answer. Okay. Any idea, anyone? If every object emits radiation of all possible wavelengths, why don't we see objects in a dark room? Fine. Consider this. Suppose there is let's say a person is speaking. Okay, I got some answer. The intensity of waves or number of waves might be less. Okay, that is correct. Correct. Suppose a person is speaking. Now, if you are close to the person, you'll be able to hear what the person is speaking. But as you go far away from the person, the volume, okay, means the intensity of sound decreases, and beyond a certain distance, you won't be able to hear what the person is speaking. Does that mean the person is not speaking? No, person is speaking. Does that mean no energy is reaching you? Very less amount of energy is reaching you, so less that your brain cannot uh, perceive it. Fine. Like we have thresholds. Fine. Thresholds means limits. If the incident energy is above that limit, then we can perceive the rods and cones. Like okay, when it comes to vision, rods and cones. When it comes to hearing, the what is that? What is the membrane which vibrates inside the ear called?
Timpani.
Okay, fine. But in layman terms, eardrum, I think it's called the eardrum. Correct only, no? Okay, fine. So there needs to be a certain minimum intensity of sound for the eardrum to vibrate sufficiently enough for us to perceive the sound. Okay, so we have thresholds. Not just we, any machine that you make also that is created also will have a certain threshold. It may be more sensitive than human, but it will also have limitations. Okay, so if the coming back to light, if the visible light that enters into our eyes is below the threshold, we won't be able to see the object. Okay, that is why we don't see objects in a dark room, even though they are emitting visible radiations. Okay, so basically, what happens? At room temperature, no. Object will be emitting radiation of all possible wavelengths. But most of the wavelength or most of the energy emitted by an object at room temperature will be low energy radiation, infrared. Very less visible radiation will be emitted by it, and even lesser ultraviolet radiation will be emitted by it at room temperature. Okay, room temperature is around 300 Kelvin. So if you plot a graph, okay, this graph is important. On the x-axis, let's say there is temperature in Kelvin units. Okay, temperature of the object. And on the y-axis, let's say there is energy emitted per wavelength. Means how much of the energy emitted by it corresponds to a particular wavelength. Okay, and wavelengths we will split. Okay, wait, on x-axis it's not temperature. Let's take wavelength itself on the x-axis. Wavelength denoted by the symbol lambda. Okay. Now, suppose the object is at room temperature. Most of the radiations emitted by it will be in infrared range. Okay, so a lot of energy will be emitted by it through wavelengths which are greater than 700 nanometers. That doesn't mean it doesn't emit wavelengths less than 700 nanometers. It does emit wavelengths in the range 400 to 700 visible range. It does emit radiations in the range less than 400 also ultraviolet. Okay, but most of the energy released will be through infrared waves. So let's split the wavelength axis into three parts. This is 400 nanometers, and let's say this is 700 nanometers. Okay, starting from 0. So if you consider an object which is at room temperature, basically what happens, it does emit wavelengths of all possible values. Okay, it does emit radiations of all possible wavelengths, but most of the energy emitted by it will be due to infrared radiations. So this is how the graph would look. What graph is this? On x-axis, you have wavelength, obviously. On y-axis, we are denoting how much energy is released corresponding to that wavelength or with that wavelength. Okay, so less than 400 is ultraviolet, 400 to 700 is visible, beyond 700 nanometers of wavelength is infrared. So most of the energy released by an object whose temperature is about 300 Kelvin, okay, room temperature, will be in infrared range. That's why we humans will not be able to see it. Okay. If you raise the temperature, we know that the object first turns red hot. Okay, as temperature of the object increases, at a certain minimum temperature, the object starts appearing red to us. What does that mean? As you raise the temperature, the peak that is there, okay, means the wavelength which corresponds to most of the energy emitted shifts to the left. So as you raise the temperature, what happens is the graph changes somewhat like this or becomes somewhat like this. So now the peak at a certain temperature falls in the visible range and it is shifting from the right side to the left side. So the first color that you will see corresponding to 700 nanometers is red. Okay, that is why as temperature increases, the object first appears red to us. As you further raise its temperature, most of the energy emitted by it will correspond to other colors in the visible region. For example, if you continue raising its temperature, it may appear yellowish in color. We observe this also in daily life. Okay, like the case of a metal rod itself. When it's sufficiently hot, it appears yellow. When it's much hotter than that, if you continue raising the temperature, the peak will keep shifting to the left. Okay, then it will even turn blue. But the metal should be strong enough to withstand those temperatures. Most metals melt, okay, by the time they turn yellow. Okay, so you may not see them turning blue, but with gases it is possible. Okay, especially the flame that you see from a gas stove, it appears blue. Okay, you all must have noticed this. Basically, I asked you this question also, what is flame? Flame is nothing but gas molecules which are at very high temperatures. Okay, at a particular temperature, the molecules appear red. At an even higher temperature, they appear blue. At an even higher temperature, at a particular temperature, the gas molecules appear red. At sufficiently higher temperatures, they appear yellow. And at even higher temperatures, gas molecules turn blue in color. That is why the flame from a gas stove is usually blue in color, because the molecules are at such high temperatures. Fine. And if you continue raising the temperature at sufficiently high temperatures, what happens is the object emits most of the radiation in the ultraviolet range. Okay, the peak will shift to the ultraviolet range of the spectrum. Spectrum is nothing but distribution of wavelengths. Okay. Then what will happen? The object will again become invisible because human eyes cannot detect ultraviolet radiation. So at room temperature in a dark room, the object is invisible to us. Raise its temperature in a certain range of temperatures, the object will be visible to us because it emits most of the radiation in the visible range. But for that, some minimum and maximum temperature are there. But if you raise the temperature even further, the object will again become invisible in a dark room because it will be emitting ultraviolet radiation and we won't be able to see it. Fine. So, what are the things you need to remember from this? Every object at any temperature more than 0 Kelvin will be emitting radiations of all possible wavelengths. But some wavelengths will dominate. Okay. Usually at room temperatures, the wavelength which dominates falls in the infrared range. So even though the object is emitting visible light, we won't be able to see it because it's not emitting sufficient amount of visible light. The intensity is too low. Okay. Then as you raise temperature of the object, the wavelength which corresponds to most of the energy emitted decreases. Okay. So at some temperature, the object starts becoming visible to us, even in a dark room. As the wavelength decreases from infrared range to visible range, the first wavelength that appears to us is 700 nanometers. So the object appears red to us. As that peak wavelength means wavelength corresponding to most of the energy released. Okay. As the dominant wavelength decreases, it may appear, it may turn yellow, it may turn blue, and then the object can disappear also because then it will be emitting energy in the ultraviolet range or radiation in the ultraviolet range. That doesn't mean it doesn't emit radiations in the other parts of the electromagnetic spectrum. It does, but the intensity won't be sufficient. We won't be able to see it. Okay. So as temperature increases, the wavelength corresponding to most of the energy emitted decreases. Okay. This is what we call as Wien's displacement law. Okay. Very important part of this chapter and very important to understand nature also. What happens in nature. Okay. Now, the wavelength which corresponds to most of the energy emitted, let us call it as lambda max. Every object emits all possible wavelengths, but one wavelength will be responsible for most of the energy radiated by it. That wavelength is what we are calling as lambda max. Okay. So let me mention that here. Lambda max is the wavelength corresponding to most of the radiation emitted by an object. So what this scientist Wien concluded is that lambda max is inversely proportional to temperature of the object when temperature is taken in Kelvin units. So as you raise the temperature, as T increases, lambda max decreases. That is what we observe in this graph also. Okay. So at approximately 300 K, lambda max falls in the infrared range. Continue increasing the temperature. Lambda max starts decreasing. We can even tell from Wien's law, we can even tell what is the corresponding, what is the temperature when an object turns red hot. We can tell what is the temperature when it appears yellow. What is the temperature at which it appears blue or violet also you can tell. Now, lambda max is inversely proportional to temperature. That means their product. Okay. Lambda max multiplied with absolute temperature. Temperature, when it is expressed in Kelvin units, is called absolute temperature. This must be a constant. Okay. The proportionality constant. And this is called Wien's constant. Let me just look up the value. in SI units, Wien's constant, usually denoted by the symbol small c, it is about 2.9 into 10 to the power of minus 3. And you can see on the left hand side, lambda max multiplied with T. Okay, wavelength corresponding to most of the energy radiated multiplied with temperature in Kelvin. So the unit for Wien's constant will be, wavelength is a length, it will be in meters, temperature is in Kelvin. So meter Kelvin. Fine. Like by mistake, you may read it as millikelvin because small m is a subscript used to indicate milli 10 power minus 3. But understand that Wien's constant is a product of wavelength and temperature. So it is meter Kelvin, not millikelvin. Okay. So this is the formula for Wien's displacement law. Lambda max multiplied with absolute temperature is equal to 2.9 into 10 power minus 3 in SI units. Very useful uh, law, you can say. Has many practical applications. Based on the temperature of an object, you can tell what is the wavelength corresponding to maximum energy radiated by the object, or the reverse. Based on the wavelength that it is emitting. Okay. I mean, all objects emit all wavelengths. Based on what wavelength it is mostly emitting, you can estimate the temperature of the object. This is how non-contact thermometers work. At the starting of this chapter, we had discussed this point. Okay. We started discussing heat with a discussion on thermometers, temperature and thermometers. Okay. There we discussed mercury thermometers, which are based on thermal expansion. But these days, non-contact thermometers are very common. You point the thermometer at the object. Without contact itself, it can estimate the temperature. This is what this is what such thermometers are based on. Basically, a non-contact thermometer has a sensor inside it, which can detect what is the wavelength that it is receiving, wavelength of radiation that it is receiving. So suppose you point the thermometer at the forehead of a person. Okay, the forehead of a person will definitely be at a temperature more than 0 Kelvin only, room temperature, or maybe more than that, body temperature, or higher than that if the person is having fever. So based on the temperature of the person's body, a certain wavelength will be responsible for most of the radiation from that person's body. That thermometer has a sensor which can detect that wavelength. Okay, which wavelength is giving me more energy? It can detect that. And based on that, using this formula, it estimates the temperature. Okay, hope this is clear to all of you. So you need to remember that all objects emit radiations of all possible wavelengths. Some wavelengths dominate, or one wavelength dominates. One wavelength will be responsible for most of the energy emitted. Based on that wavelength, you can estimate its temperature. Okay, and based on that wavelength only, you see the object emitting a particular color. For example, if there is a metal rod which has turned red hot, means wavelength corresponding to red is dominating. If there's a metal rod which has turned yellow, it means wavelength corresponding to yellow is dominating. So based on that wavelength, you can estimate temperature. So I want you all to apply this formula. First question. Estimate the temperature at which an object turns red hot. You know the wavelength corresponding to red, no? 700 nanometers. Nano means 10 power minus 9. Okay, keep that point in mind. Estimate the temperature at which an object turns red hot. Do this, all of you. I'll give you 2 minutes. You may use a calculator if required. Okay. So it is given to you in the question that the object has turned red hot. Means the dominating wavelength is the wavelength corresponding to red. That means lambda max is approximately 700 nanometers. Nano means 10 power minus 9 meters. Okay. Based on that, we'll have to estimate its temperature. We know lambda max into T is 2.9 into 10 power minus 3. So T becomes 2.9 into 10 power minus 3 divided by 700 into 10 power minus 9 can be written as 7 into 10 power minus 7. Okay. So adjusting, we'll take this as 29 by 7 into 29 means 10 power minus 4. So effectively becomes 10 power 3 Kelvin. 29 by 7 is 4.1 in that range. So the temperature is close to 4.1 into 10 power 3 Kelvin, means around 4000 Kelvin, an object turns red hot. Okay, 4000 Kelvin means on the Celsius scale, how much it will be? Like 0 Kelvin is minus 273 degrees C. Okay, from Kelvin temperature, you subtract 273, you will get Celsius temperature. So 4000 Kelvin in Celsius scale, if you want, subtract 273 from it, it will still be quite close to 4000. Okay, 3700 something. So at that high temperature, around 3700, 3800 degrees C, an object starts turning red hot. Okay, so you can show that in this graph. For it to reach this temperature, okay, or for it to emit red radiations, the temperature should be approximately 4000 Kelvin. Okay, and that is the temperature that you see there from those objects which are red hot. Even flame, okay, it has such high temperature. Okay, you can even estimate the temperature of the sun. What color does the sun appear to be? Is there a particular color which the sun emits? Like from your everyday experience, I want all of you to answer. Mornings and evenings it appears red, afternoon it appears yellow. Basically, sun uh, emits all colors. Fine. Yellow is the dominant one. Now, why does it appear red at some times? That is due to refraction, okay, scattering of light. Many phenomena are there. You learn in the chapter optics, okay, wave optics, not right now. But sun emits all visible wavelengths. It emits ultraviolet, it emits infrared also. But basically, it appears yellow. When all light from the sun is allowed to reach us, it appears yellow. So, based on the wavelength for yellow color, you can estimate the surface temperature of sun. Core temperature of sun will be much higher. Surface temperature can be estimated. Okay, by using this same formula, lambda max into T is equal to 2.9 into 10 power minus 3. Okay. So basically that is what is Wien's displacement law. So what all have we discussed so far in today's class? We talked about absorptive power. Okay. Basically, when electromagnetic radiation means electromagnetic waves are incident on a surface, some of them are absorbed by the surface, some energy is absorbed by the surface, some energy is reflected. So out of all energy incident, what fraction is absorbed is what we call as absorptive power. So for a perfect absorber, which means a surface which absorbs all the energy that falls on it, absorptive power will be equal to 1. For a perfect reflector, it will be 0. It doesn't absorb anything. Okay, so it will be 0. Then we talked about radiation emitted by an object at different temperatures, and the next formula we discussed is Wien's displacement law. Okay. Next idea. Now, even in a well lit room, okay, some objects appear black. Why are some objects black? Is black a color? Technically, is black a color? Think about this, all of you. Even in a room which has white light, some objects appear black. Why? Okay. Sohan is saying that we see black when no visible wavelength is emitted. Okay. Almost correct. Fine. So suppose there is an object and let's say white light is incident on it. Let's say, assume this is a multicolored object. Assume white light is incident. Now I cannot show white light here, so I'll show it somewhat like this. So let's say white light is incident everywhere on this object. Fine. Assume some part of this object is blue. What does that mean? It reflects blue colored light, absorbs the other colors. Assume some part of this object appears red. Okay, it's a multicolored object, as I said. Assume some part of it appears red. That means it reflects red color. It absorbs the remaining colors. Fine. Maybe some part of this object is yellow colored also. That means from white light, which is a combination of all colors, it absorbs the remaining colors and emits yellow. And finally, let's say some part of this object is black. What does that mean? Black is actually not a color at all. In everyday life, we call black as a color. But if no visible light comes from a particular direction, then our brain perceives black in that direction. Obviously, there's nothing seen. Okay, so basically, black is the absence of visible light. Okay. In fact, while sleeping, it is easier to fall asleep when your eyes are closed. Or even if you want to relax your eye, you close your eye. Okay. That is because when eye is open, no, visible light will be entering into your eye. It will be automatically disturbing the rods and cones. But when you close your eyes, it appears black. Means there is no light going into your eye at all. So rods and cones will not have to oscillate. Eye will relax. So black is the absence of radiation. Okay. Absence of visible light. Fine. If nothing is reflected by an object, nothing means I should be more specific here. If no wavelength in the visible range is reflected by an object, the object appears black. Okay, so remember, black is the absence of visible light. Fine. So objects which appear black to us, basically what they are doing is they are absorbing all visible light. Means they are absorbing all the wavelengths in the range 400 to 700 nanometers. They don't reflect any radiation in that range. That's why they appear black to us. Okay, hope this is clear. Does that mean, see, absence of visible light is black, that's okay. But even if an object is reflecting infrared radiation, it will appear black to us because our eyes and brains are not designed to perceive infrared radiation. Okay, the rods and cones that are there in our eyes, they don't oscillate to infrared radiation. Okay, they don't send any information to the brain. Similarly with ultraviolet also. The same happens with ultraviolet also. We cannot see such radiations. Okay. So the usual black objects that we see around us, they don't reflect in the visible range. They may be reflecting in infrared range. They may be reflecting in ultraviolet. They may be emitting their own radiations also in infrared and ultraviolet. They will definitely be emitting actually, not maybe. We just discussed that any object at room temperature will be emitting radiation, most of which falls in the infrared range. Okay. So if you switch off lights, okay, or if you enter into a dark room, you won't be able to see anything, not because there is no radiation. You won't be able to see anything because there is no visible radiation. There is infrared radiation. You cannot see that. Okay, we humans cannot see that. Okay. So let's talk about absorption and reflection itself, not emission by the object. Now, the usual objects that we see around us, some of them appear black because they absorb visible light. They don't reflect visible light. That does not mean they don't reflect infrared. It does not mean they don't reflect ultraviolet. They could be reflecting those wavelengths. In fact, they will be. No surface in real life is a perfect absorber of all wavelengths. Okay, remember this. No surface in real life, or I can say no real surface, is a perfect absorber of all wavelengths. They may absorb some wavelengths thoroughly, but some other wavelengths will definitely be reflected. Okay. Now, hypothetically, or we can imagine a surface which absorbs all wavelengths. Okay. So, hypothetically, we can consider a surface which absorbs all wavelengths. Such an object, okay, an object which absorbs all radiations incident on it. Okay. Such hypothetical objects, they are given a name called black body. Okay, it's called a black body. So they don't exist in real life. Normal black objects are not black bodies. Fine. Black body is an idea actually. It's a perfect absorbing surface. It absorbs ultraviolet, visible, as well as infrared radiation. Any radiation that falls on it gets absorbed. Such an object is called a black body, or such a surface is called a black body. Fine. So, as I said, this is a theoretical idea. Everyday black objects are not black bodies. Why? Because the objects that we see black in color in daily life, they are absorbing visible radiation, but they will definitely be reflecting infrared radiation, and maybe some ultraviolet radiation also is reflected by them. We cannot see it. We cannot see infrared, ultraviolet, so the object appears black to us. So everyday black objects are not black bodies. Okay, black body is a scientific term. It is the name given to a surface which can absorb any radiation that is incident on it. Okay. So we'll stop today's discussion here. In next class, we will talk about radiation and absorption by a black body. Okay, there are certain laws governing that. Okay, so at a certain temperature, how much energy does a black body radiate? How much energy can it absorb? Okay, what happens to the black body due to this radiation and absorption? Those things we'll discuss in tomorrow's class. Okay, thank you all. We'll continue tomorrow.